Welcome to my Siggraph Asia 2021 talk, Dynamic Neural Garments. I am Meng Zhang, a postdoctoral researcher at Smart Geometry Processing Group, University College London. I co-authored this paper with Tuanfeng Wang, Douglas Lin, and Niloy J. Mitra. There is a strong desire to synthesize virtual characters with plausible and rich garment details for games and VR applications. A popular workflow is to model the garment dynamics with a physically based simulator and render the resulting mesh sequence with texture information and environment illumination. However, if a change in the viewpoint or the underlying body motion is desired, one has to iterate over different components of this workflow. In this work, we present a new method named as dynamic neural garments. With the input of body motion plus a camera viewpoint, our method directly estimates the dynamic appearance of the detailed garments and generates realistic image sequences. Physically based simulation provides an accurate way to model garment dynamics, while the computational efficiency still depends heavily on the complexity of garments they operate on. In recent years, researchers have also explored the use of deep learning methods to learn how garments deform under body motion. However, these approaches model the garments integrated with the body shape and are limited in terms of modeling the complex garment dynamics. Some recent works augment a low resolution of the garment with plausible wrinkles. Those approaches are highly dependent on the quality of the coarse garment input. Accessing accurate geometry is helpful to enable various control over the lighting, texture, and the geometry. But handling 3D garments with varying topologies and sewing patterns in a unified learning framework is still an open research problem. Furthermore, post-processing is often required to handle potential collisions and penetrations. It motivated us to overcome those cons by aiming at synthesizing the plausible garment appearance rather than the geometry. Image-to-image translation methods have shown incredible success recently in terms of translating images from a particular domain to another. Meanwhile, neural rendering are processing an exciting breakthrough, where deep neural features are learned for controllable image synthesis, including viewpoint change and modeling deformations. Here we classify those methods with respect to three factors whether used in their processing, that are Coarse 3D, neural features, and motion cues. However, most of these approaches assume humans wear tight clothing and do not explicitly focus on very dynamic motion sequences. Our work aims to fill this void by presenting a novel neural rendering pipeline to render plausible dynamics for loose garments that generalizes across motion changes and view variations. Inspired by the work of DNR, short for deferred neural rendering. Given a motion sequence, we first predict a 3D deformed coarse garment proxy. Then we jointly learn neural features on the coarse template and train this neural render. We expect that this neural render is able to synthesize the dynamic appearance of the target garment. For the coarse garment prediction, we first adopt an autoencoder to learn the compact representation of the coarse template. Next, we learn a motion encoder to map the encoded motion information to the corresponding latent representation of the coarse template. Same as DNR, we built dynamic pairs of neural texture sampled on the predicted coarse garment and the ground truth image to train this network. This experiment shows that the dynamic details are blurred by directly adopting DNR to synthesize garment appearance. We also use other baseline methods to synthesize a garment appearance. The coarse 3D here, we use a coarse garment predicted by our introduced method. This quantitative evaluation indicates that firstly, motion cues play an important role to capture the dynamics of the loose garment under body movements. As we can see here, V2V is the strongest baseline method. Secondly, having coarse 3D geometry helps with the generalization across motions and viewpoints. The performance of EBDN drops behind some methods that are using 3D coarse template. And third, learnable neural features augment the generative ability to synthesize structures from a very coarse proxy, since DNR produces the most reasonable skirt outline that resembles to the ground truth. Therefore, in our work, we present a new architecture to synthesize dynamic garment appearance to combine all those three factors. Now let's go deep into our rendering network. Firstly, we define dynamic neural maps as the input of the rendering network. Second, we introduce a temporally coherent encoder with implicit consideration of the temporal and spatial coherence between consecutive frames. After the encoder, a new layered-based decoder is connected to decode the dynamic appearance of the target garment from the latent code and to harmonize it with the background rendering of an undressed 3D character. And last but not the least, we introduce a temporal and spatial discriminator to train our rendering network adversarially. Now let's take a look at the detail of the architecture. The input of the rendering network is two consecutive frames of descriptor neural maps. The neural maps are formed by concatenating the learnable neural texture as introduced in DNR. And the dynamic motion features incorporated by a sequence of the relative distances between the current frame coarse garment to each joint and of the past frame motions. For the detail, please refer to our paper. The motion features aim to provide the information of post-specific appearance changes of the target garment. Our encoder network consists of a set of convolutional layers that encode the input neural descriptor maps into latent codes. To implicitly achieve temporal consistency between the latent codes of the consecutive frames, we use a spate block to normalize the target frame latent code with the coherence information of its previous frame. Specifically, we shift and rescale the normalized latent code of current frame by the new mean vector and the standard deviation learned based on the consecutive latent codes. Connected with the encoder, our layered-based decoder consists of a set of conv transpose 2D layers symmetric to the encoder. Given the latent code, these layers first generate a feature image and its corresponding mask. In order to composite the garment with the character body and the background, we introduce a layer blending module to blend the garment features with background features. We finally apply two residual convolution blocks to refine the results and generate the final rendering. With the output of the rendering network, we train a discriminator network that takes consecutive frames as input and classifies them as real or fake. We provide two types of input to the discriminator. The first one is a target frame rendering conditioned with its previous ground truth rendering. And the second is with known the next frame ground truth rendering to tell the current rendering to be real or fake. Our adversarial loss ensures the spatial temporal plausibility of the renderings. In summary, we present a dynamic deferred neural rendering network based on the intermediate Coarse proxy to synthesize varying motion appearance with the target colors and textures. Now let's compare the results of our method with a basic DNR. For fair comparison, we train a version of DNR adversarially with our discriminator. Obviously, ours achieves the best result with smooth structural coherence between frames, even without the motion cues. We also compare the generalization ability of our method with other baselines. For unseen motion sequences, our method also achieves the best result with reasonable garment structure and distinctive dynamic details. In this table, we quantitatively show that our method outperforms all those baselines with both the seen and unseen motion. In summary, our work aims at directly synthesizing the final garment appearance starting from a 3D body motion sequence. We first predict how a coarse 3D garment template deforms under the influence of the motion. We then learn deep neural features on the coarse garment template that capture both the geometric differences between the template and the target garment as well as dynamic appearance changes. Finally, we render these features from a desired viewpoint to synthesize the final appearance of the target garment on a 3D character with plausible and rich dynamic details. The key of our work is that we present a new dynamic rendering network to synthesize varying motion appearance with the target colors and the textures. We introduce the dynamic descriptor maps as input of the network composed by learnable neural features and dynamic motion features. We implicitly solve the structural coherence between frames by our temporally coherent encoder. And finally, we train our rendering network with a temporal and spatial discriminator. Now let's see some of our results. Firstly, we test the generalization ability across unseen viewpoints. When training our network, we randomly sample 10 viewpoints for each training example, compared with the nearest viewpoints retrieved from the training set. Our method can generate temporally smooth image sequences for the target garment. Here we demonstrate the generalization capability of our method for unseen motion sequences. Note that for all three target skirt styles, we use the same plain long skirt as a coarse template. Here we synthesize full body dress with an unseen motion sequence. Given the dynamic neural rendering network trained for a thin body, we can fine-tune it to generalize across different body shapes. Please note how different garment outlines and wrinkle patterns are synthesized based on the underlying body shape. Our method can be trained with real video sequences to synthesize the dynamic appearance of real garments. Finally, our method can be combined with 3D body motion estimation methods to guide the synthesis of the garment appearance based on the actor's performance. Our work has limitations. Here we list some of them. Firstly, our rendering network is scenario-specific. We generalize our method to different backgrounds by fine-tuning our layered-based decoder. In order to more precisely control the lighting and texture effects, in the future, we can extend this method to synthesize pixel-wise geometry information rather than just RGB colors. Secondly, although our rendering network composites the synthesized garment with a target body that already resolves most of the collisions in the final rendering, between the garment and the body, occasionally certain collisions may still remain unsolved, especially where the depth ordering is highly dynamic. We resolve this in post-processing. For example, here, we first identify the arm regions in the character body renderings and the garment region in the final rendering. If the arm is closer to the camera but the arm region is occluded by the garment region in the final rendering, we bring it to the front as shown here. In the future, we can jointly learn the depth ordering maps between the garments and the body as a constraint to solve the collision artifacts. The third one is that some artifacts in temporal and spatial consistency can still be observed, especially in the results of unseen motion sequence. While the garment appearance generated by our method for each frame is plausible. To solve this problem, it is a promising research direction to further explore additional temporal network like RNN, transformers, and recent advances that focus on the texture sticking issue, such as alias-free GAN, to achieve more temporally, spatially coherent results. Additionally, we can go deeper to explore new motion descriptors as the input network for better motion generalization. Finally, we would like to thank all the reviewers for their constructive comments, Adobe Fuse for providing us a virtual character and Mixamo for the motion sequence. We also want to show our gratitude to Jinglong Yang and Stapeng for their helping on the comparisons. This work was partially supported by the ERC Smart Geometry Grant and gifts from Adobe Research. That's all for this talk. Thank you for your attention and listening.